Well, we've just been talking about it's clearly been a bunch of words and a bunch of explanations, but pictures really tell a much clearer story in terms of what's taking place. And so we're going to now walk you through a number of animations that will just give you a much clearer idea of how this fascinating pressure phenomenon starts to create interesting effects when it gets to be really on a global scale, or even on sometimes very interestingly on a local scale as well. What we have here is a container which we're imagining is holding water, representing by this blue at the bottom. The water is going to have some weight when it's acted upon by gravity, and what we clearly have as the first instance is that weight has got to be resisted, and so we've got a force that's coming down. If this is going to stay within the container, this buildup of this hydrostatic pressure within this container has to be resisted by an equal and opposite resistant force, which is this force in the bottom, the force that the bottom of the container will experience. And this weight needs to be supported, and that pressure is fairly uniform, and so there's going to be a resistance force which is fairly uniform, which is what is associated with this presence of this water or this buildup of this fluid and this weight within this container as well. So that's a pretty basic idea. It gets more interesting, of course, as we imagine adding more water, which we're pouring in from the outside. Obviously, during the time of pouring, there's going to be a momentum flux at the surface, and this pressure is going to be disturbed from this normal hydrostatic linear effect, but we're going to ignore that for now. But during the time of motion, where this fluid is no longer being resisted, it's flowing out from this open end of this container, we're going to have a buildup, and as we do, we get this linear increase of weight within this container. And now we're at this full part. We've got this much larger accumulation of weight, a much larger static pressure at the bottom of the container, and therefore a much larger resistant pressure that has to support that. And this is going to be supported either by a container or by the presence of more fluid. And as we've mentioned, if this is a matter of a scale difference of a meter or two, we're going to have a certain degree of accumulation. But if we're going to have an accumulation that could take place over 1,000 meters or even over 10,000 meters, we're going to have the kind of pressures that are characteristic at the base of the ocean. If we have an accumulation that takes place over thousands of kilometers, then we have the kinds of pressures that are consistent with planetary scale phenomenon. And if they accumulate over hundreds of thousands of kilometers, or even perhaps over millions of kilometers, we have the accumulation that's typical of a star system, where the pressures are so great that we can actually collapse nuclei together and produce this process of atomic fusion. So we have that accumulation. If there is a significant change in the density or the specific gravity of the fluid, then this straight line accumulation that we've shown here for small distances becomes somewhat curved, and we get a even larger increase associated with a change in density, which is of course what happens in the atmosphere, that the lower levels are compressed, and so the buildup of pressures are much more rapid near the surface than they are above the surface. And we have that thinning in the atmosphere that's characteristic of compressible fluid. We have argued that pressure reflects an accumulation of weight above the surface that we're considering the pressure for. That's pretty straightforward in that kind of container that we looked at, but it starts to generate some very fascinating possibilities that we'll begin to see now in this animation. What we have here is a container that we're visualizing as being full of a liquid like water, and we've got two corks or stops in openings in the side. And what we're going to do, of course, is we're going to let the animation run, and we'll take those corks out and see the effect. And what we're going to see, and I think you can, I'm sure, visualize this quite easily, is that the pressure is lower at the upper level and it's higher at the lower level. So we're going to have different pressures being visualized. We argued that pressure reflects the accumulation of weight, so that's obviously going to be reflected here. But we also argued that pressure acts in all directions. And I think it's pretty easy to see that the weight is a vertical force, but if we open this opening up, if we remove this cork, we're going to clearly get a horizontal flow. And that pressure in the horizontal direction, that difference between the outside and the inside, is going to induce a flow. So pressure difference causes flow, pressure acts in all directions, and static pressures become dynamic pressures or pressures associated with flow when we have an imbalance. And this is, of course, something that's straightforward. We're going to try to be neat, so we're going to put a container in here that we can hold the water. And at the point that this begins to open up, we'll just pause this animation again and just sort of see what we're going to get for a visualization. So at this point, this hydrostatic drawing again will illustrate the accumulation of pressure associated with the weight above that particular point in the fluid. But what we clearly have is the low pressures at this upper port produce a relatively small jet or a small stream that sort of lazily drops off, which I'm sure you can visualize, and this pressure at the middle of this represents a much stronger jet, and there would be a larger discharge associated with that we haven't bothered to show in this animation. And clearly now the fluid is accumulating. The fluid that was on the left is moving lower and to the right, and this is something I'm sure that you're all used to visualizing. If we let this animation continue, we're at the point where the level is almost dropped to that first port. Obviously, when it gets to that level, that first flow will stop, the second flow will continue until the time that it reaches its port, and at which point the animation clearly has reached its termination and there's nothing further to see. So we can stop it at that point just before that last dribble occurs. So what we clearly have is that the accumulation of pressure that takes place statically is potentially available to be turned into motion. And what we need is a connection or a communication that exists between the two ports, and we need to have the possibility of flow, which needs to be supplied by some source. So we've got the second idea of motion potentially being associated with an imbalance of forces, and that clearly pressure does act in all directions, as one can easily see if they were to reproduce this simulation with something like a plastic container that we knock two holes in the side at different levels, and you'll be able to visualize quite easily the same things that we're illustrating here. Our third pressure animation involves this new connection where we've got two different amounts of fluid on two different containers that are directly connected to each other. So now there isn't going to be so much an absolute difference in pressure in terms of there's a completely different elevation, but there's going to be a relative difference. And so we're going to fill up these two sides of this container. So we're going to end up with a high pressure side and a lower pressure side, which again we can animate or we can visualize with this difference in the pressure triangles on either side, representing a smaller buildup on the lower side and a larger and deeper buildup on the other side. So we'll fill this up to its full position. When we've emptied both of those containers, figuratively speaking, at this point we've got the significant pressure difference on the right hand side compared to the left hand side. And clearly what we're going to have is larger forces, and so the container on the right, by having to hold a larger depth of fluid, will have to be stronger. It's going to have to withstand greater forces than the one on the left, which has a smaller amount. We have a communicating connection between these two things, which in the atmosphere may be just adjacent air, but we're visualizing in this case as a pipe or a conduit that has a closed valve initially. And what we're going to do, of course, is we're going to open that valve up, figuratively speaking, and start to allow flow to take place. So at this point now we start to get a direct communication. If these two pipes were to have exactly the same properties, the same valve, there would be a difference in the flow in this particular case because of the difference in the pressure on either side of the system. That the head difference or the pressure difference between the right and the left is different between the two sides of this container. But once this level reaches the level of this connecting pipe, then the head difference in that case would go to the same value, and the flow rate actually would go to the same value as well, which we won't prove, but will simply state as a consequence of the effect of pressure when we add flow to the equations. And what's happening as a result of this communication, of course, is the system is now moving towards an equilibrium. And that equilibrium is associated with having equal levels on both sides. So we'll let this thing run through one more time, and we'll stop it before the animation restarts again in order to establish what that equilibrium value is. The pressure difference at both levels of the outlet is going to cause a flow. The flow is going to tend to address that pressure imbalance so that it's going to be reduced over time as the pressure builds up on the left and is decreased on the right hand side. And that's going to produce this tendency towards an equilibrium value.